Okay, so for question 7, we start by identifying the characteristic equation, and then we find the roots of the characteristic equation. The roots of the characteristic equation gives us the form of the general solution. Once we have the form of the general solution, we can apply Euler's identity to convert it into a trigonometric function, or a function with trigonometric components. And then we can apply the undetermined the process of undetermined coefficients to this process of undetermined coefficients to solve for the particular solution, where this is the general form of the particular solution. And we use that to solve for first A1 and A2, and then for this particular solution of y. Then we just substitute y of p back into our general solution that we solved for, and in order to solve for C1, C2, and C3, we just find the first, second, and third derivative, substitute, and then just solve for that systems of equations to get C1 of -1/16, a C2 of 16ths, and a C3 of 0. You can see our final solution is 1/8 times t to the t squared plus 1/16 cosine 2t minus 1/16. Number 5, we can leave things in their integral form, so it's a little bit shorter. Once again, we find the characteristic equation, r cubed minus r squared plus r minus 1. And the roots of the characteristic equation are plus or minus I and 1. That characteristic equation gives us the form of our solution, which is C1 e to the it plus C2 e to the negative it plus C3 e to the t. From there, we apply Euler's identity again, just like on the last one, and we can replace our negative i's with, or our plus and minus i's with trig functions. There's a bit of additional algebra there, but next we solve for the Wronskian, as well as the determinant of sort of the individual Wronskian for each component, or for each term. Once we have the Wronskian, we are straight away able to write everything out into integral form of the particular solution, where this is the integral form of y of p for y1, this is for y2, this is for y3. You could solve all these out, but the problem is to leave them in integral form, so then you can just take your particular solution and substitute into the general solution. And so you wind up with this whole solution here, C1 cosine t plus C2 sine t plus C3 e to the t plus the integral 1/2 times negative cosine t plus sine of t, all in parentheses, times secant t plus dt, or dt times cosine of t, where cosine of t is y1, plus the integral of 1/2 cosine t plus sine of t times secant t dt times sine 2, plus the integral of 1/2 e to the negative t times secant t dt e to the t. I'm pretty sure that the particular solution integral of e to the t 1/2, or for y1 and for y2, those are solvable. But I think that the solution to e to the t, there's no solution to that integral, so you can leave it in integral form. But I left the whole thing in integral form because it's the problem size. All right, thank you.